the
Now it's live.
Now it's live.
Now it's live. Well, while you search for a lower third, I'll say, hey, everybody. Actually, I should search for a lower third.
Yes, you should.
What kind of a hypocrite moderator am I if I command you to find a lower third, and yet I'm not able to find a lower third on my own?
It's so good.
Lower third. Okay. Perfect. Hey, Pamela. Yeah, I have less hair. I'm just embracing my Patrick Stewart, my Jean-Luc Picard.
Except you have this large beard going, so it's like you're the love child of Riker and Picard.
It's my Neil Stevenson look.
Okay.
But yeah, hey. So where are you?
I'm down in Houston, Texas, home of NASA Houston. Clearly, NASA Johnson Space Flight Center. I'm on the north side of Houston, though, where they are holding the Lunar and Planetary Sciences Conference. And it's between sessions. I'm tweeting planets, planets, planets. You may have slightly worse quality in the Hangout this week than normal because I'm recording onto my handy-dandy Zoom. And so it's not going through the computer at all because this I can travel with. My other mic is sort of like bolted onto my desk, and my desk doesn't fit in my luggage.
Whenever I try to take this thing through the security in the airports, I always get given the third degree. Like, what is that? It's a microphone. It looks like I know it looks like a bomb. It's a microphone. I promise you. But yeah, they give me a hard time. Cool. So, Lunar Planetary Society. So, have there been any?
No society, just conference. This is a NASA-funded conference.
Right. So. You're not in like Houston. It's like a little town, right?
The Woodlands. It's basically a hipster community, for lack of a better way of putting it. Extraordinarily affluent. I've seen cars here. I've seen nowhere else other than the posh parts of London, with lots and lots of very environmentally sound parks and large businesses, which is ironic because they're building really large facilities for a lot of the oil companies around here.
Right. Well, they deserve it. So did you? So have there been any interesting announcements?
So far, no. The thing that has a lot of us verklempt is tonight's NASA night. And there's a lot of things on the table. Just what missions are getting canned, what are getting kept. Is the Lunar and Planetary Institute staying where it is in Houston? Is it moving to Tucson? Do we have any news on a lot of things? And what's interesting is this is the meeting where back in 2012 they basically said we're in sequestration. This is what it means. We found that out at this conference. And this year, everyone sort of hit the zen point of, meh, we'll either have jobs in 5 months or we won't. And
what are you going to do?
To see an entire community sort of like, nah, they're either going to fire all of us or not. That's where we're at, which is a sad place to be at, but I guess it's better than 4 years. So we've moved past the tears to the, well, what's your second career?
Right. Exactly. What's your backup plan?
Yeah.
Yeah. Okay, well, let's get rolling. So, for those of you who have no idea what it is that you've stumbled into, this is an episode of Astronomy Cast, our weekly facts-based journey through the cosmos. We will be taking about half an hour to record the show, and then we'll stick around and answer your questions about space and astronomy. Not only the questions which you are asking us live, but also the questions that maybe you've emailed into us. So, I'm going to say hi to Guido Bibra, James Oliver, Jim Meeker, Helga Burkog, Giselle Sabarin, Nancy Graziano, Steve Chisnell, David Duthet, Thomas Traniker, Michael Delmer, Tom Van Scotter, Tony Lynch, Tom Nathy. Did I say Nancy Graziano? If I hadn't, I really should. Nancy Graziano. I already did. Okay. So, hey, to all of you. Those are all the people who happen to be using the Q&A app and said hello. So I just wanted to give you guys all a shout-out. And one thing that I forgot to do last time, I think, to mention is just the very cool communities that we are honored to be friends with. So there's, of course, the CosmoQuest community. Go to cosmoquest.org/forum, or you can go to the WSH crew, which is on Google+, and it's a really great community. Hardcore, super fans of the shows. A lot of the people whose names I just mentioned there are big contributors to the forum. So I just want to suggest that you go to those two locations. How ready are you, Pamela?
I simply have to press the button and make sure that it actually is recording data, because currently it says no data. So I'm pressing
That just means
record.
There's nothing on the card right now.
It says key hold. What does key hold mean?
That means you've pushed the hold button down.
So
move it away from the key hold button.
Aha! I have released it. I clearly have not used this toy in quite some time.
Make sure you press the. Make sure it's on the microphone and not on the 2 line inputs. Hold on, let me just look at her device here. That's good. And then you're going to want to press the record button once to get a sound level.
Testing, testing. I have the sound levels. They are happy sound levels.
Okay, great. And then you press it again, and then you're recording.
It is recording. Hi, Preston. I'm using a new toy. Please don't hate me if this audio is weird.
I spend a lot of time with that Zoom. You could probably tell.
Yes.
Because we do it. That's what we do for all of our shows, all of our videos. We use the Zoom.
Okay.
It's a wonderful thing. If you want to record video and you want to record good audio for the video, get that device that Pamela just had. It's the Zoom, the XFN.
Yeah.
4. Yeah. Terrific device. Okay, cool. I'm going to press record as well, so it is happening.
Hi, Preston. Fraser.
Hello, Preston.
We're sorry. There's much discussion of audio equipment.
All right, here we go. Let's start. Astronomy Cast, episode 370, Kaufmann, Bucherer, Neumann experiments. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing, and where are you?
I am with a crappier video camera at the Lunar and Planetary Sciences Conference down in the Woodlands, Texas, which is a little tiny enclave on the north side of Houston. Sadly, about 45 minutes away from the Johnson Space Flight Center, but this is a much nicer conference venue than the one that we had down near Johnson. So this is where I am, and we're discussing planets with some asteroids and other rocks thrown in all week long.
And for those of you who don't know what this is like one of the big conferences. We have the American Astronomical Society meeting. We have the AAAS. We have this one, and then like the Geophysical
The American
Society.
Geophysical Union.
Yeah, and those are sort of the big 4 meetings. So you're at one of the big 4 this year, and a pile of press releases will come out. And we're going to find out all about subsurface oceans and hydrothermic vents and potential landing spots on Mars. So this is going to be exciting. Keep us posted. Okay, cool. So any other announcements this week?
Just reminding everyone, our Hangout-a-thon is set for April 24-25. If you are a super fan living in the greater St. Louis area or willing to get your butt there, we even have some opportunities for you to either volunteer or hang out as we record. We certainly need all hands on, well, everything as we go. So drop me an email, drop me a note wherever you are. We're looking to celebrate making a new day work for science, and the fact that these Hangout-a-thons have kept us going. This, as I was saying before we started recording, this week marks the week that we learned about sequestration back in 2012 actually, and it's only because of your donations that I'm still here. So Thank you for allowing me to keep having my career as we've faced numerous government cutbacks. cutbacks.
All right, so as we're thanking people for giving us a chance to have a career, I should also point people at the way you can help fund what I do, which is to go to patreon.com/universe today. And this is, of course, the Patreon campaign that we run for the Universe Today, and also the videos that we do. We just recorded video number 172. We release 2 of them every week, all about cool concepts in space and astronomy, many inspired by what we do here on Astronomy Cast. I'm not going to lie. So yeah, go to patreon.com/universe today, and then you can help fund what I'm working on.
And to mimic what they say on NPR, we're here because some people have chosen to donate, and if you've never donated, you're basically leeching off of the goodness of others.
Oh, yep.
Be one of those people yourself and give today.
Go ahead to patreon.com, check out what my salary is. You can see you can see what I earn.
Yeah.
Okay, well let's get rolling. So one of the most amazing implications of Einstein relativity is the fact that the inertial mass of an object depends on its velocity. That sounds like a difficult thing to test, but that's exactly what happened through a series of experiments performed by Kaufmann, Bucherer, Neumann, and others. All right, so Pamela, where do you want to start? Do you want to start with just this idea? What are we talking about in relativity when we talk about the inertial mass of an object depending on its velocity?
So the basic idea, as misarticulated over and over again, is that an object's mass gets larger and larger and larger the faster it goes. Now the truth is that if you increase me to near the speed of light, I'm not actually going to add atoms to my body. I'm not going to become more massive. I will do that perfectly well on my own thanks to chocolate. Speed of light is not required. Now, what will happen is my ability to interact with the world as an object with mass will seem to increase. How I move, how much energy it takes to increase my velocity will go up. And the way we actually look at this nowadays is not by saying something's mass increases, but by saying that we see a change in its momentum, and we refer to it as this concept of inertial mass, which is tied to the energy required to increase or decrease something's motion.
Now, when we talk about some of the concepts of relativity, a lot of it is relative, right? So, for example, if you're traveling at the speed of light towards me, as we talked about last week, your length on the distance of direction traveled seems to change, but it's a relative thing. You're moving towards me. I'm in theory not moving, although really, So with this sort of change in the inertial mass or change in the momentum, how is this relative? Like if we've got two things that are moving at the same speed, do they see this of each other?
You usually refer to it as relative to the frame that you accelerated out of. So if two things start out in the same frame of reference, this is the twins example you often read about, and one of those twins starts accelerating, he's the one that we look at in terms of seeing that change in mass. Now, if the two twins are going along in some frame of reference, it's not like one of them can appear to decelerate out of that frame of reference. So this using the which one is accelerating as figuring out whose mass is changing relative to whom's is usually a safe starting point.
Okay, and as you mentioned, though, this is not about your mass increasing.
Right.
This is about your inertial mass or your momentum. And so can you sort of explain what the difference is there?
So any given object in motion has momentum. This includes light, which has no mass. The momentum can either be written out relative to kinetic energy. So kinetic energy is 1/2 mv squared. Sorry, that is not kinetic energy. Kinetic energy, I just blanked, totally. That is kinetic energy. Never mind, I'm sorry, I'm having a Monday.
1/2 mv squared. I recall that formula.
Yes, kinetic energy is indeed 1/2 mv squared. Momentum is mass times velocity, so just mv. So you can get between these two different quantities. And with light, we don't know its mass, but we know its energy, so we substitute that in. Since all light moves at the speed of light, you look at the energy of the light. instead of the kinetic energy, and you can get at the momentum. It's all maths, just canceling m's and v's and factoring in c's. But that only works in your standard Newtonian mechanics. You have to start adding in factors related to, depending on what you're manipulating, one usually often minus the velocity divided by the speed of light. And that reduces to just 1 if
you're going the speed of light.
Yeah, if you're going the speed of light.
Right.
And it's actually the square root of 1 minus v squared over c squared is what you often see in these equations.
Right.
And so if you're dealing with something that essentially reduces to 1, you ignored it in normal day-to-day.
Right. You'd have a 1. Okay, so then let's sort of rewind back and let's talk about before these experiments were run. What was the expectation by the researchers on sort of what was going to happen or how the universe worked?
Well, they didn't really have much at this point. So we're looking at what was going on in the 1890s and the earliest 1900s. In 1896, Henry Becquerel, whose last name I hopefully actually got right this time, realized that a lot of different elements seemed to give off these high energy, we called them beta particles back then, which much to my dismay, I learned at some point in high school were actually just helium particles, and I felt betrayed by everything because everyone talks about how exciting beta particles are, beta radiation. No, it's just fast-moving helium. But he didn't know it was fast-moving helium when he found it, so they called them beta particles. And these beta particles were fairly easy to capture. They also found via beta radiation that there were often high-energy electrons that were given off during the processes that led to various decays. Again, those are easy to capture and deal with. And they still didn't fully understand the electron back then. If you think about it, this is before people were dealing with electricity as a day-to-day thing that powers every device around you. Experiments involving electricity had gone on for a long time. You can imagine all the things Benjamin Franklin did a couple hundred years before this. But the details of understanding how to deal with electricity were completely new. So J.J. Thomson came along, and he realized in the late 1890s that you could actually change the path of an electron with magnetic fields, with electric fields built up by non-moving charged plates, and started calculating if you have charged particles moving through these different fields, how does one electric field affect one charged particle, how does a magnetic field affect a moving charged particle. And all of this led to a series of equations that made it possible to calculate the expected trajectory of a moving charged particle with a given velocity as it moved through electromagnetic fields. This is actually something that up until recently everyone dealt with every single day. Cathode ray tubes, the technology that led to the television coming out in the 1930s, all of that was based on this early work by Thomson on moving electrons around with electromagnetic fields. So they were building early cathode ray tubes, shooting electrons, applying fields, and based on the fields that they created, they could move that electron around. Essentially, if they wanted to, they could make a very slow picture because they didn't have all of the electronics that are required for television.
Right, but the point here is that you're starting to learn how to control the direction using electricity of very fast-moving particles.
Right, and the thing that they ran into is you can calculate for a slow-moving electron moving through one of these setups. Very straightforward what the expected deflection is. You can also use this if you know the velocity of the electron, you know the charge of it. You can, well, you don't even have to know the charge. You just have to know the velocity of the electron. You can get at the charge to mass ratio based on how the electromagnetic fields deflect its path. So you have an electric field, you have a magnetic field, you have a known velocity, and now you can get at the charge to mass ratio. And what they found was if that velocity got high enough, as the velocity increased, the charge to mass ratio changed. And in fact, it changed such that the faster you were going, your charge is getting held constant, your mass isn't increasing, but it seems to be increasing. So as that m goes up with that charge above it, your entire ratio goes down.
And so to just kind of understand, like I'm imagining them shooting electrons past magnets, and they're trying to control the angle that I'm making all kinds of hand signs, so you in the podcast are just going to have to imagine me shooting these beams of electrons with my hands. My hands are electron beams. Right, so you've got these electrons, and they're turning this corner as they're going past the magnets, and then they're going towards the cathode ray tube. The faster you speed up these electrons, you would expect them to be harder with more momentum to kind of crank them around that corner and aim them where you want, but it got even harder than they were expecting.
And they didn't have the high sensitivity equipment we have today, so in order to precisely figure out what was going on, they'd use essentially gated systems that only allowed electrons with certain velocities to go through the system. And then they'd have to look to see where on a photographic plate those flung electrons were able to escape to.
Oh, so smart.
Yeah, it was really amazing equipment that they put together. And so then they got left with this, well, what's going on with this apparent increase in mass, decrease in measured charge to mass ratio, as this object is moving faster and faster. And of course you had experimental error that played in, and you had really awful algebra that played in, and this led to about 10 years of people going, and Kaufmann, who's one of the people that we're talking about today, is actually one that in trying to put all of this stuff together, he did very complicated experiment, complicated equipment, precise measurements, and goofed his algebra in trying to explain all of it, because he was trying to deal with how that ratio of velocity over the speed of light seemed to factor into everything they were doing. And of course, if you have an algebra mistake, you come out saying, well, what I did doesn't actually match what was theoretically predicted, which is a really interesting result, except it's based on an algebra fallacy. So he came out with a result in 1901 with math errors, corrected it, came back out in 1902. But then also, while he did a very good experiment and he did good photographic plate measurements, it still wasn't ideal. And so they were left in this situation in the early 1900s where there are a couple of different explanations. Lorenz had figured out how to work his, he moved from contraction due to your motion relative to the luminiferous ether, so contraction of length in the direction of motion. He kept going. He figured out how to factor in increase in mass as velocity approached the speed of light. He came out with all of what we still call the Lorentz transformations. Wrong physics to explain it, but excellent maths to explain it. There were other folks. There's a fellow by the name of Max Abraham who came out with a set of equations to try and explain how things had to take into account both a transverse electromagnetic mass and then your normal. And so people were coming up with all sorts of different ways of manipulating the variables to take into account, well, maybe it's because you're moving in this direction versus all sorts of different things. And they also started coming up with things like, well, we know the electron's a sphere. Now imagine if the charge is distributed on the surface, but that somehow gets affected. They were grasping at straws.
Right, so like that the shape of the electron changes in the, like it turns into a football shape depending on the direction of motion, and
Or
that would
maybe only the
change.
charge moved on the surface.
Right.
So the beginning of the century was kind of a mess.
Simpletons. Come on.
Well, they weren't simpletons. They
No,
were
I know, They didn't know. They
people.
were just thinking
Yeah.
of ideas, right? What could cause this weird change in the mass charge beyond of what we were expecting?
I'm just kind of like amazed that anyone came up with the idea of let's add and subtract and square root factors of 1 plus v over c, or 1 minus v over c, or 1 minus squared v over c. That is such a weird factor to come up with, but they did it. So there was a lot of stuff that in retrospect I can only ask who came up with that idea, because it worked. And once Kaufmann figured out his math error in 1902 and fixed it, everyone was working to replicate these experiments. Everyone was working to figure out how do we do better so that we can sort the difference between these different theories. And Einstein was meanwhile off to the side. He wasn't in the lab running experiments. That was never really Einstein's thing to do. He was instead off to the side thinking. And while Lorentz was coming up with his contractions and trying to figure out how to deal with the experiments related to the luminiferous ether, while Kaufmann was flinging electrons around, while Thomson was trying to understand the atom and the electron, Einstein was trying to figure out what is special about looking at the universe in terms of the speed of light. How do we perceive the speed of light? Why is it that different colors of light all appear to move at the same speed? How can that be possible that you see the same speed of light regardless of what direction you're moving in or how fast you're moving? And as he thought and as he worked on amazing maths without algebra errors, I'm sure he had some, he just failed to publish them.
Right.
As he worked on all of this, he realized that the key wasn't that there was some ether we had to figure out how we are or are not coupled to. The key was the fact that everyone perceives the speed of light the same way. And in order for that to be true, you have to start changing how you perceive different things. So as you're going faster and faster, your perception of time changes. Well, if your perception of time changes, how is it that the person on a high-speed train who drops a vase sees it break, and someone who's off to the side watching the train go by, where they see everything on the train in slow motion because time isn't moving at the same rate in both situations, how is it that they see this vase slowly float down to the platform and also break? Well, you explain that by increasing its mass. So all of these different Lorentz transformations all factor back to how do you explain two observers seeing the same things happen even though they perceive time passing so differently.
And I never had thought about that idea of the vase falling in the train, and the fact that because of the relativity you see it breaking in that way. That's really cool.
And it leads to so many things suddenly being able to be made sense of in what we observe. My favorite is the poor innocent muon. It's a high energy particle that's extremely unstable, forms in our upper atmosphere via high energy reactions and particle decays, but we're able to detect it down at the surface of the planet. And the amount of time that it takes that muon to get from where it's formed to the detectors, often in our college classrooms, is longer than the muon should be allowed to live. And so clearly some magic is allowing muons to reach the surface of the Earth. And that magic's relativity, because the muon is moving so fast that time is slowed down for it, and it is for us able to live longer, even though in its frame of reference it lives the same amount of time.
That's crazy.
It's crazy awesome,
Yeah.
is what it is.
Yeah, that's like a science fiction story, I think. Some scientist needs to extend her life, and so she starts moving faster and faster than, nearing the speed of light, and therefore gets to live to see her children grow up or whatever. I don't know.
Or lives to see the disease that she has
Get cured. Yeah, exactly. Oh, that's perfect. Hey, any science fiction writers? We just came up with your great idea.
Yeah, but they had this in Ender's Game. They had to proceed. I can't remember the character's name.
Don't you spoil it.
I'm not spoiling anything with this part. So basically, they had to save one of the people to mentor Ender until they found him. And so this person essentially skipped through the generations waiting for the right child to be born. And they did it by keeping him going a very lonely life near the speed of light.
At high speeds, at relativistic speeds, yeah. That's really cool. Cool. So then, even after sort of those initial experiments were done, I know they kept going. Other people kept performing the experiment with greater and greater levels of accuracy. But now it's a matter of testing and confirming what Einstein had worked out separately.
Exactly. And it was also initially, we had equations that had things blowing up previously. There was what was referred to as the ultraviolet catastrophe, which we talked about in our black body radiation episode, which was the original maths to try and understand essentially what colors of light are given off in different scenarios. Said that you should get a whole lot more ultraviolet light than is actually being observed. And we eventually used the fact that we knew ultraviolet light was not actually coming out in infinite amounts to realize that light must be quantized, must have discrete energies, and that changed the equations. With all of the electron charge to mass experiments, they seem to indicate that if you went faster and faster and faster, your mass would go to infinity, which seems like a rather bad thing to happen. And so that you have to keep wondering, if I go fast enough, if I try this with different other things, will I see that starts to turn over? There's all of these, I want to prove Einstein wrong. That started from day zero.
People have been trying to do this for centuries.
Well, no, a
Two
century.
of them.
A century and 10. 1905 is when things came out.
I said two. Between 1 and 2 centuries, people have been trying to do this.
It still rounds to 1. Anyways, different argument. So what was found is, by gosh, yes, as you go faster and faster, it's true, your mass does show no signs of stopping its dramatic increase.
And this just makes it impossible to go faster than the speed of light.
It makes it impossible to actually get to the speed of light.
Get to the speed of light, and not to mention go faster.
Yeah, there's not enough energy to do it.
Yeah, that is, Einstein has really ruined sci-fi Christmas.
No, because he did nothing to ruin the idea of tunneling. So we know that electrons can tunnel from one place to another. Electrons have mass. They're essentially jumping through space and ignoring the intervening places. We just need to figure out how to tesseract.
Right. Okay. All right. Well, then you're off the hook this time, Einstein. Well, thanks a lot, Pamela.
My pleasure.
All right. Let's see.
Okay.
I had a good idea for another experiment that we could do, which is I just did one of the videos that we just wrapped up was on CPT Symmetry.
Mm-hmm.
And that might be, there's an experiment that in 1980 Nobel Prize was proving CP violation.
Okay. Email that one to me. I haven't read about that since.
Yeah.
Last time I read about violations of that accord was 2002, so I'm sure that things have changed. There's so much cool stuff
They did their experiment in 1964.
Okay.
Yeah.
Then I simply have no memory of what I read about in 2002.
The gist is well, I think that's when they proved CPT. But anyway, the gist was that, they wondered if you could you have an antimatter universe No, because the weak nuclear force shows a preference for left-handed.
I don't remember what the T is. It's
T is
color.
time.
Oh, okay.
Right? And so then could you do parity? So could you hold up, all particles in a mirror? No, because same thing, the weak nuclear force causes a problem. But could you do both at the same time? Could you have antimatter and a mirror universe? No, because, and then this is the experiment that these guys did, was to show that in fact you still couldn't have both at the same time. And it wasn't until you inverted time as well that you can invert everything and get the universe to work exactly the same way. And it's only by running time backwards. So if you see everything in a mirror, you reverse the charges of all particles, and you run time backwards, the universe unfolds exactly as it would in the forwards way, which will be indistinguishable from anybody either way. So that's a great experiment. It's a great line of reasoning about mirror universes and all that kind of stuff. You have no idea what I'm talking about, do you?
Well, my brain is also, no, I have an idea of what you're talking about. My brain is also going through what's the next cool session that I'm not at right now because I'm recording.
Now, do you need to go, or can you stick around for a couple of minutes?
I can stick around for a couple of minutes, yeah.
All right. Let's get a couple of questions out. We'll go from there. Everybody says hello from wherever they are. So
Hi.
I'm just going to just merge that all together. Hello, everyone, from all the places that you are. Jim Meeker says, Pamela, let me check with my family. I may be able to drive down and help out with the Hangout-a-thon. So
that would be awesome, Jim.
Jim is one of the sort of most busy posters to the WSH community. He posts a zillion space stories. Steve Chisnell asks, do relativistic gravitational lenses bend different wavelengths of light at different angles? Put another way, do gravitational lenses impart chromatic aberration? Good question. Do you want me to rephrase that? Were you still looking at?
No, I'm thinking. I don't know the answer to that one.
So we know that gravity. I guess does gravity bend? Does the effect of relativity, of the mass, space-time distortion of mass in space, affect the wavelength of the light? Can you separate? Will you get gravity's rainbow?
Yeah. Well, so the amount of the size of the mass that you're rising out of does shift different amounts of energy. You have different amounts of gravitational redshifting depending on the mass that you're escaping from. So the question is, if you have white light, so you have a whole rainbow of light, are those different colors going to get shifted different amounts? And the answer would be yes, because you're starting with a different color, so you're going to get a different color. Am I answering the right question, or am I answering a sideways question?
If you had white light coming around the mass of a black hole, would the different wavelengths of radiation in the white light get pulled apart, just like so differently, or do all photons get turned the same amount? And I'm guessing it's the same because. When we see we see distortions around the photon sphere, and we see.
I'm going to say actually the answer is no, because they have different amounts of energy. So different colors have different amounts of energy. Different amounts of energy, and again, this is me working in my head, and I want to confirm this. Different amounts of energy relate to different amounts of momentum, which means that their paths should get shifted different amounts.
Richard Summers asks, given tragedies happening during normal spaceflight reentries, can such vehicles not use a much longer and shallower reentry path that does not lead to skipping out of the atmosphere as they do so?
I think that they're using pretty much the shallowest they can.
Yeah, they're using the optimal reentry thing they can. I mean, as you slow down, and I highly recommend you play Kerbal Space Program if you haven't already, you hit the atmosphere hard.
Yeah, and if you're at the wrong angle, you come out the other part of the atmosphere and you miss the planet Earth.
Right, and you just skip off and head off into, well, especially if you're coming on like this, this translunar
Yeah.
injection fluid coming around the backside of this, and you're coming back to the planet, you've got a ton of velocity you've got to shed, and if you don't, you skip off the atmosphere.
Mm-hmm.
For the space shuttle and such, you're not going to skip out of the atmosphere. You're in orbit.
Yeah.
But as you move into the atmosphere, it picks up, right? The amount of atmosphere that you're pushing through ramps up really fast, and just heats up and speeds up speeds up and heats up your spacecraft. Guido Bieber notes that was almost too heavy science for 8 to 9 in the evening, so I can't think about a coherent question. Let me just ask you this. Have you met up with Emily Lakdawalla at the conference?
Yeah, we've already run into each other. We talked yesterday. I think we were covering different sessions today, which is actually good because it means we got to tweet out different things. Yeah. Her tweets I love to look at because she actually, my brain periodically goes, you're using words, I have to Google, pause while I Google the words that they're using, because I'm an astrophysicist, and when you get geologists up there talking pure minerals coming out of their mouth, I have to look up words to figure out why what they said was meaningful. But she doesn't do that.
You've met Emily Lakdawalla.
Oh yeah, several
times. Yeah. Yeah.
It was at this conference several years ago that was the first time I met her, and she explained to me why olivine matters. And it was one of those conferences before everyone had internet in their pocket, and all of the scientists were like, olivine, 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 and I had no clue what it was other than something that made pretty jewelry.
Okay, Steve Chisnell says, that's the wrong question. I wasn't talking about Doppler shift. I was talking about gravitational lensing. We were talking about gravitational lensing.
Yeah, so with gravitational lensing, you have a high mass object, you have a light ray moving past it, the light ray gets bent, and the amount that it gets bent is going to depend, if it's not light, if it's a normal object, it depends on its velocity, its momentum. With light, the momentum is related to its energy, and it's always moving at the speed of light. So, yeah, all of these things play in together. I think the effect of the color is going to be unobservable, microscopically small, just sort of like me slingshotting past Jupiter versus Fraser slingshotting past Jupiter on identical trajectories. We don't have the same mass. And so, according to the mass, we will have minutely small differences in outcome, and I'm not sure that those are detectable changes in outcome.
Okay, so Guido Bibra notes, hey, everybody, follow Emily Lakdawalla, Lakdawalla, so on Twitter. So that's exactly right. Lakdawalla, and of course, while you're doing that, follow Pamela at Starstrider with a Y. And what the hell? Me, F. Cain.
Yeah.
I'm the easy one to remember.
You're the one that takes up the least characters. The rest of us are kind of stupid.
Smart. Okay. Graham Stickings asks, what about tachyons?
No.
Okay. No. You can't just do that.
Theoretical particle, not yet having any evidence that they exist, other than Star Trek uses them and abuses them. So I'm simply going to go no and stop my explanation.
Graham says, is Fraser referring to the Cobalt-60 experiment? Let me see. Maybe I am. The one with the Nobel Prize? Yes, that's the one. No, that's the Wu experiment.
We're both apparently having an indecisive day.
Beta decay of Cobalt-60 in 1964. Yes, that's the one. There you go. We want to do that one. It's super cool. Just this idea, right, of it's so science fiction-y, talking about mirror universes and antimatter universes and time going backwards. It's fantastic. Amar Stadler asks, could the Lorentz contraction due to motion be interpreted as an example of space being somehow buckled into a fourth spatial dimension? Buy Lorentz soup. We cram more into our cans. Awesome. So I guess the question is that as you're seeing this the contraction.
Yeah, I don't think we worry about it that way. That is how we talk about like the different aspects of an electron being rolled up, so that you see spin up or spin down, and the rest of the electron is in other dimensions. In this case, I think we're actually just looking at following along with everything that Einstein said, that it's a geometric change in the shape of the universe.
Yeah. David Joseph Wesley asks, what science fiction gets relativity right or closest to right?
All of Orson Scott Card's stuff, you can have all the other issues you want with him. All of Orson Scott Card's Ender series books get it right. The Hyperion books get it right. Those are just the ones that are coming to mind immediately.
Was it Old Man's War?
Old Man's War gets it right.
Yeah. But there was one where...
A lot of them get it right.
Yeah, and in terms of movies, Interstellar did a great job of handling relativity. Once Kip Thorne had explained that, in fact, the mass of the supermassive black hole in the movie was like 3 billion times... Like, it wasn't a stellar mass black hole. It was a incomprehensibly massive supermassive black hole. More massive than any we're really super familiar with. There was I'm trying to think. Stargate has done it. I don't know. Relativity.
It's one of those things they tend to get right more often than not because it's awesome.
Yeah.
So they pay attention. And all right, now I'm reading some stuff by Kim Stanley Robinson that's pretty interesting. They actually use the relativistic correction to Mercury's orbit to understand an act of terrorism. So that was kind of cool.
Forever War is the one that I was thinking about, not Old Man's War. So Forever War was by Joe Haldeman, and right. In that, essentially the soldiers are sent at relativistic speeds, and so they're literally at war for thousands of years, to the point that they're forgotten about by the people who initially sent them out, and it's just great. It's really well done.
For strange
throw in the
values,
comments. All of you, throw them in the comments. I'm sure you.
I do need to get going in the next.
You got to run.
Or so.
Okay.
Yeah.
Well then, yes. Go. Let's wrap this up. Hey, thanks, Pamela, for taking time out of your busy schedule and doing some actual some science there. Say hi to all of our good friends from all of the fans of Astronomy Cast, and we will see you next week.
And I will be on the tweets giving myself more carpal tunnel, and I hope to see you all online.
All right, have fun. Thanks, everyone.